All right, hello again. So last week we were looking at some applications of solving differential equations. What did we look at? Some mixture problems and I believe exponential growth and decay problems. So this week we want to look at two other types of problems. Both of these are really not too bad. Today in particular, lecture 9 is in particularly not a bad problem at all. So it deals with the temperature situation. So think about with me just the change in temperature with regard to time. So in general, I'm trying to model the change in temp with regard to time. So don't let the big T and little t confuse you. Big T is temperature, little t is still time. All right, so what things impact temperature? Well, I like to drink coffee, so my coffee cup, if I drink it out of a styrofoam cup, it may heat or cool differently than maybe a ceramic cup. So the cup itself plays into that. My office, our air conditioner, when it works perfectly in our building. So my office is generally a constant 71 degrees, give or take a little cycling on the thermostat or whatever. But that outside temperature also impacts the temperature of the room or the building or something of that nature, impacts the heating and cooling of things. So in general, we say that there's some constant, and that constant could be, say, the insulation in the building. It could be the insulating factor of the coffee cup or whatever it is I'm looking at. And the other things that impact it are we say M of T, which is, for lack of something better to call it, I'll call it the outside temp. That could be the temperature of the room. It could be it could be the temperature of the sun shining through the window or something of that nature. And then big T, of course, is the temp of the object, which is really what I'm trying to model. So this is our model that we're going to start with each time. We're going to turn that into a differential equation because of these rates of change and solve it. And so I apologize for number 1 being at a Baptist University. It's a problem I stole from a book. We'll say a cold beverage initially at 35 degrees warms up to 40 degrees after 3 minutes while sitting in a room of temperature 70 degrees. How warm will the beverage be if left out for 20 minutes? So again, I'm trying to model this temperature of the beverage at any time t. And so the important piece to us is this idea of the room temperature. We assume that that's a constant temperature, so that's going to be our outside temperature, for lack of something better to call it. So here we go. Change in temperature with regard to time is equal to 70 degrees minus, and I'm just going to leave out the big T of little t just so we can work with it, 70 minus t. So that's the d that I want to solve. And it looks like it's separable. I can get all of these t terms with d of big T, and I can get d of little t with this k by doing some cross multiplying. So I can divide both sides, and I can multiply both sides by d of temperature. So what I end up with is a d that looks like this. D big T is equal to 70 minus big T is equal to k d little t. All right, so I think that's is separated. I think I can integrate both sides now. Be careful with your integration. This looks like a u prime over u situation, which is going to end up being a natural log. Be careful with your u's. So I need a negative sign in there. So this becomes a negative natural log 70 minus big T equal, And on the other side, I'm integrating little t's. I believe that's going to just be a k little t plus some constant of integration. All right. I don't like that negative sign in front, so let me take care of that negative sign by dividing through by negative. And I'm going to pull a little trick that's going to drive you insane. So k is some constant insulating factor or what have you. It's not really going to change, is it? So a negative k is negative k, but I don't know what the constant c is equal to. So a negative constant is still some constant. If you want to call them different things, you're welcome to do that, 1 and 2. All right, so I want to get rid of the exponential now, or the logarithm rather, by exponentiating both sides. We've pulled this trick lots and lots of times. This is a negative k, e to the negative kt plus c, which is really e to the negative kt times e to the c. And we've dealt with that a couple of times. E to a constant is simply a constant. So let's finish solving that for big T. That's what I'm trying to model, isn't it? So I can subtract 70 from both sides. And divide through by a negative. So I end up with the temperature as a function of time. This constant divided by a negative is still a constant. This number divided by a negative is a positive. And I'm just going to flip-flop their places. So this equation models the temperature of the function at any time t. Let's go back and use some of these initial conditions and see if we can find, we need to find c, we need to find a value for k. So it says the cold beverage initially at 35 degrees. So I know that the time at, the temperature at time 0 is 35. I also know the temperature after 3 minutes is 40 degrees. So I'm going to start with the temperature at time equal to 0. So if I let t be 0, that's just e to the 0 power, which is just 1. So I'm left with just this equation. So it looks like c is a negative 35. So my function now looks like big T at little t is 70 minus 35 e to the negative kt power. So now I'll make use of the other condition to find k, and my other condition says that the temperature was 40 degrees after 3 minutes. So let's solve that. So I can solve that by my calculator handy. Subtracting 70 from both sides. I can divide each side by negative 35. Excuse me. So I'm left with an negative divided by negative is a positive 30 over 35. You can reduce that to what, 6/7 is equal to e to the negative 3k power. So I can get rid of the e by taking the log of either side. And finally dividing both sides by negative 3. So in my calculator, I have the natural log of 6 divided by 7, and then that quantity divided by negative 3. So it looks like my constant here, I'm just double checking to be sure I'm getting the same answer on the other side. Apparently I am. 0.0513 maybe, or 14 is what I'll use for K. So officially, my temperature function looks like what? 70 minus 35e to the negative 0.0514 t power. That function describes the temperature at any time t. So the question for us was, what is the temperature after 20 minutes? And so I'll fill that in my calculator. So here we go. Get it where you can see everything. So 70 minus 35e to the negative 0.0514 times 20. And it looks like 57 point some change. I'll say 57.5. Approximately maybe 57.5 degrees. And so that's the answer to this problem. That's nice, isn't it? And they're not difficult to solve. You've got to know some things about logarithms. You've got to know some things about the exponential function. But the model is what I want you to see. So be thinking about those models. We had a model last week. We've got a model this time as well. So look at number 2. Number 2 says, on a hot Saturday morning while people are working inside, the air conditioner keeps the temperature inside the building at 24 degrees Celsius. At noon, the air is turned off, and that's really when this problem starts, is at noon. The air is turned off and the people go home. So the initial temperature is 24 degrees when the air is turned off, Celsius, of course. The temperature outside is a constant 35 degrees for the rest of the afternoon. If the time constant for the building is 4 hours, and that's kind of a funny thing, is we're going to represent the time constant as 1 over k. What will the temp inside the building be at 2 o'clock and at 6 o'clock? And then when would it reach 27 degrees? So again, my model for this problem is some constant k times the outside temperature minus the temperature of the object. And so the outside temperature is the sun in the building, right? I'm talking about heating the building. And the temperature outside is a constant 35 degrees. So there is my differential equation. I will make a note of some initial conditions here. So we're letting at 12 o'clock is when this thing starts, which is going to be when time is 0 and the temperature at time equal to 0 is 24 degrees. And then it says, what else does it say? Actually, I don't think I need another condition because I was given my constant k. So if I've worded this a little bit awkwardly, and I apologize. This is the time constant 1 over k. So actually, for my problem, it's 1/4 35 minus t. In the previous problem, we were given some information to solve for k. Here it was essentially given to us. So let me solve this differential equation. Again, if I solve it like I did a second ago, then I have this dE that I want to integrate. Again, think about your U substitution business going on here. This integrates into a negative natural log of 35 minus t equal to 1/4 little t plus some constant of integration. All right, so again, if I multiply through by negative or divide through by negative, I have a negative 1/4 t and then still some constant, some new constant. Don't let that bother you. That bothers lots and lots of students. They're constants. I don't know what they are. this is not the same as this. I just carrying along that C, of course. So if I exponentiate both sides now, then I'm left with 35 minus big T equal to e to the negative 1/4 t plus c power. And we've pulled that same trick lots and lots of times. Right, if I separate this, we're using my properties of exponents. That's just an e to the c, which is nothing more than a constant. So some constant times e to the negative 1/4 t power. And again, I'm going to subtract 35 from both sides. And multiply through once more by the negative. That makes this 35 be positive, and it makes this term be still some constant that I don't know about. So there's my differential equation to be solved. So I'll go back and use that initial condition that says at time equal to 0, the temperature is 24. So a negative 1/4 times 0 is 0. E to the 0 is 1. So it's this equation that I want to solve. And it looks like C is going to be a negative 11. So again, my differential equation then looks like T at T is equal to 35 minus 11 e to the negative 1/4 t power. All right, so that models the temperature for us at any time t. And so the first question is, what will the temperature be at 2 o'clock? So we want to find t at 2. I'll leave that for you to find, but I'll go back and put in an answer. I want to find the temperature at 6 o'clock. Again, that's just plugging in that value in place of t. It's the last question that I'd like to think about. When will the temperature reach 27 degrees? Let me just give you I've worked this problem earlier, and so t at 2 is 28.3. You can go through and see if you can get that. T at 6 is 32.5 degrees. And the reason I wanted to mention that is if I'm interested in 27 degrees, then I know that's going to happen at some point between 2 o'clock and 6 o'clock. Okay. Actually, no, I take that back. Sorry. 27 degrees is before 2 o'clock, isn't it? All right. So the last question says, when will it be 27 degrees? So I'll say, all right, 27 is equal to 35 minus 11 e to the negative 1/4 t power. So let me subtract 35 from both sides. Let me divide both sides by a negative 11. Let me get rid of e by taking the log of either side. And finally, you can divide both sides by negative 1/4. I'm going to multiply both sides by negative 4. So that should be my value of t. And again, it should be before 2 o'clock, isn't it? Because at 2 o'clock it was a higher temperature. So negative 4 times the natural log of 8 divided by 3. Oh, and I've got an error somewhere. Where did I said 8 and negative 11. It's a difference of 3. That's division in it. Sorry. 11. Sorry about that. I had my head around subtraction. So make that correction on your paper if you're working with me. So again, negative 4 times the natural log of 8 over 11. So it looks like 1.27, which is about 1 1/3 of an hour. So I guess the time is about what, a third of an hour is 20 minutes, so about 120 is when that's going on. Okay. So you can use some estimation there to be able to evaluate that. It's actually not as far as 120, but T being 1.27 hours is certainly sufficient for that. All right, so I'm going to post a couple of homework problems for these, and so work through those. Start with the model every single time. By the way, you can have other things that affect the model. We're not. But I might have, some heating or cooling other source going on in there. Sometimes people have to take into account like the light fixtures or something of that nature that also heat the room. But our problems will all work like this.